Hello everyone, and thanks for listening to my presentation. I'm Yusuke Takahashi, and I'm a graduate course student in the Civil Engineering Department of Osaka Institute of Technology in Japan. Today in my presentation, I'd like to share the latest findings of my research into the mechanical properties of steel concrete composite girder subject to thermal history due to fire. I'll start by quickly going over the introduction, the experimental, and the numerical analysis. Then, I'll discuss my results and the implications of my findings. In recent years, fire accidents on bridges frequently occur both in Japan and abroad. This figure illustrates general flow from bridge fire occurrence to restoration. This figure shows the relationship between temperature and time. This data shows some events from fire occurrence to investigation. We defined after fire is this area. Such damage has been confirmed in bridge investigation after fire. The previous research, experiments, and analysis have been executed to establish the behavior of steel girder during fire. However, a few researches on behavior of the steel girder after fire. Hence, it takes time to investigate the passing probability of the damaged bridge from fire. Therefore, it is necessary to understand the influence of the strength reduction after fire on the structural characteristics of the steel girder bridge. Please look at this picture. This picture shows damage condition of concrete slab. Such damage of the bottom of concrete slab is often confirmed damaged investigation after fire. The concrete slab and steel girder are composited with headed stud. However, this damage may be decreased the degree of composite. Therefore, we focus to the composite behavior of composite girder bridge damaged by fire. The purpose of this study are to clarify the change of composite behavior damaged by fire, and to verify of elastic composite theory as analytical method after fire. Okay, so I've told you about introduction. Next, I'd like to show you the test specimen outline and the results of the experiments. This figure indicates side evaluation of the test specimen. The span of the test specimen was 7.0 meters with a frame exposed range of 4.0 meters. The structural performance of each condition was verified before and after fire. This figure shows the flow from the experiments. First, a static loading test was carried out at room temperature to confirm the behavior of the composite girder. Next, the fire test was carried out at the temperature distribution of the composite girder was measured. Finally, the static loading test was repeated. This figure indicates the strain distribution of the test specimen at the center of the span. This point represents measured value, and the dashed line represents analytical value of complete composite girder. This figure confirms the strain distribution was almost the same at complete composite girder. Next slide shows the results of fire tests. This figure indicates the relationship between furnace temperature and time. After the fire test, we checked the bottom of slab, and there are no cracks at the program temperature 340 degrees Celsius. However, another program temperature 680 degrees Celsius occurred some cracks. These figures show the relationship between the temperature of steel member, including headed stud and time. Also, the contour of the composite girder cross-section at 30 minutes. This figure shows at 680 degrees Celsius. The analytical value of the steel member were almost the same as the measured value. Also, through cracks formed at 17 minutes, and this picture illustrates cracking condition on top of slab. This figure shows the deflection at the center of the span. The behavior in the fire shows a relationship between the vertical deflection at the center of the span and time. At 340 degrees Celsius, the deflection of the center of the span was 15 mm at 30 minutes. No residual deflection remained after fire. At 680 degrees Celsius, the deflection at the center of the span was 40 mm at 30 minutes. After fire test, a residual deflection of 6 mm remains. This slide shows the results of static loading test after fire. As you can see, the strain distribution was almost the same as the room temperature at 340 degrees Celsius. On the other hand, the strain distribution was a tendency to approach non-composite behavior at 680 degrees Celsius because of the decrease in rigidity due to cracks that were generated in the concrete slab. So I've told you about result of the static loading test after fire. Next, I'd like to show you the numerical analysis. I'll explain the analysis formula of elastic composite theory. This equation shows general equation for change of stress resultant of the girder. These coefficients are determined by the sectional conditions and distributed spring constant. Also, these coefficients denote the reduction factor of the elongation and flexural rigidity of the steel girder due to fire. This equation shows distributed spring constant using the standard spring constant and the flexibility constant. The flexibility constant is important factor in this study. It denotes like this. Let's move on to the next slide. This slide shows validation of analytical method. These figures show slip and flexibility constants after fire. On the other hand, this figure indicates the strain distribution of the test specimen of static loading test after fire. A comparison between the measured and analytical values of strain distribution show almost the same as the measured values. I'm about to wrap up my presentation. We carried out experiments to clarify the temperature distribution and the behavior of the composite girder after fire. The conclusions obtained from the study are summarized as this. Thank you for your kind attention.